That's a lot of chapters to do.
Yep.
We're not skipping.
Yes, we are. Okay. Nate, rotate, please. Thank you. Shh, quiet, please. So, what we're starting with today is we are starting chapter 7. And chapter 7 is all about exponential and logarithms. If you're planning on going to trigonometry or calculus, you need to know this stuff. And we will review it in trig, and you also reuse it in calculus. So, even if you're going to personal finance, you guys will use exponential functions there as well. Banks with interest rates use exponential functions. Just good stuff to know. So, this is where we're starting. So today in 7.1, we are going to explore exponential models. And really what we're really going to focus on today are, they call them exponential growth and decay models. So growth is when things get bigger. Decay is when things get smaller. So that's what we're going to truly focus on today. So what is an exponential function? So an exponential function has the form y equals a b to the x. B is greater than 0, and b is not allowed to be 1. B we call the base, and the base is constant. In order to be an exponential function, the variable has to be in the exponent place. So you notice how it's up there in the exponent? That makes it an exponential function. X is the what we call the independent variable. And when we're talking about exponential functions, unless we're talking about a story problem where some things don't make sense, the domain is all real numbers. Okay, so just by knowing we have an exponential function, I know what my domain has got to be. Unless, like I said, unless we're doing a story problem where some things don't make sense. That's the only time you'll limit it, okay? So let's see what these babies look like. We're going to graph some. If you need graph paper, there's some over here by the pencil sharpener in the front. If you would like to just make a sketch on your paper, you're more than welcome to do that as well. And please, with the graph paper, it's expensive. We're almost out. Use it only for the graphing ones, all right? Don't use it for scratch paper, please. And don't take a whole bunch and hoard it. So, the first one we're going to look at is y equals 2 to the x. So, this is an exponential because the base is a constant and the variable is in the exponent position. So, this is an exponential function. And the best way to start this is actually just make a t-table. Generally speaking, these x values are good places to start. Sometimes we need to add more, but generally, if you use -2 to 2, you're going to get a pretty clear view of what is going on with the function, okay? So simply all we're going to do is plug them in, evaluate it out. So if we put a -2 in for x, we have 2 to the -2. This is why we had to learn our exponential laws and rules. We have a negative in the exponent. What does that tell me to do? Flip it. 1 over 2 squared, and it becomes positive. Well, what's 2 squared?
4.
So it's positive 1/4. So when x is -2, the function equals 1/4. So now let's put a -1 in. Uh-oh, negative in the exponent. So it's 1 over 2 to the first. Well, 2 to the first is just 2, so it's 1/2. Good job. Uh-oh, 2 to the 0. 1. Anything to the 0 is 1. All right. Now put a 1 in. 2. Put a 2 in. 4. And we're going to graph it. Quick question. Is there any exponent I can pick that will make this thing negative? No. Because what do the negative exponents do? It makes them into a fraction. So am I going to ever, if this is a positive base right here and we're not multiplying by a negative out front, this is always, our values are always going to be positive. So let's graph this baby. So -2 1/4 is like right here. Teeny tiny. -1 1/2 is like right there. There it is. 0 and 1. 1 and 2. 2 all the way up to 4. So what would happen if what if we picked 3? 2 to the third is 8. It's like way the heck up here, right? And if I picked smaller numbers, we would just get closer and closer to the x-axis. Exponential functions look like this. They get really, really flat looking out here, and they get really, really big really fast. That's an exponential function. Okay? Well, that's when the base is bigger than 1. What happens if we're smaller than 1? Let's see what happens then. It's craziness. So, example 2. So now we're going to graph this guy. 1/2 to the x. So our base is 1/2. So we're still going to use our t-table. So and I'm still going to go -2 all the way to 2. We good? And here we go. So we have 1/2 to the -2. I'm going to deal with the negative right now. When the negative in the exponent, what do I do with the base? Flip it. So instead of 1/2, it's going to become 2 over 1, which is 2. The negative tells you to flip the number. So I just flipped it and becomes positive. So what's 2 squared? 4. So let's do the next one. So we have 1/2 to the -1. So the negative tells me to flip the number, and now the exponent's positive. So what's 2 to the first? 2. Uh-oh. To the 0. 1. And then put a 1 in. So it's 2 to the 1. It's just 1/2. Oh, that's a bad 2. And then we're going to have 1/2 squared. 1/4. Ready to graph that one? Yeah, it goes down instead of going up. So at -2 we're at 4. -1 is at 2, and then 0, and then 1/2, and then 1/4. So it doesn't, I would probably say it falls. Instead of rising, it falls. This kind of just got reflected. What do you think? Can do this? You can graph these babies? Let's just make a table and plug them in. So the big objective today was to talk about exponential growth, exponential decay. What do you think this one would be? A decay. What was the first one we did? A growth. Right? Well, there's a couple little kind of things we're going to talk about here. So, exponential growth. Exponential growth. If you know it's a growth, as x increases, y increases. That means it's a growth. Exponential decay would be as x increases, what happens to y? Y decreases. And cool thing about exponentials is they flatten out, and there's a line that they will never ever cross. What will they never ever cross? The x-axis. So we call that an asymptote. When a graph can never equal something or cross, or can, sometimes we'll say it'll jump it, but this graph will never ever touch the x-axis. It will get infinitesimally close. It will get so close that our eyeball will say it has to be equal. But there's also pixel problems, like if we graphed it on a calculator, we can only see so much, right? But analytically or theoretically, it's never gonna quite touch it. It gets so close. And we call that an asymptote. An asymptote is a line that a graph approaches, but never touches. And there are two types of asymptotes. There's vertical asymptotes and there's horizontal asymptotes. Vertical asymptotes are x equals, horizontal asymptotes are y equals. And so if you looked at these guys right here, it's a horizontal asymptote that it never crosses. And what's the value of y along the x-axis?
Greater than 0.
We would say there's a vertical or a horizontal asymptote at y equals 0. Is that all right? Because it's the horizontal lines are y equals. Do the other one. So like this guy here, same thing. It gets really, really close to this line right here, which is happens to be the x-axis, but there's a horizontal asymptote at y equals 0 because it'll never touch it. It gets really close.
Can you have them where it's like y equals 4?
You can even have asymptotes in trigonometry or in pre-calculus. We call them slant asymptotes, where it follows like a line. I can show you one. Want me to show you one? Want to take a little side tangent here, talk? Okay, I need a better calculator. Wish this had a Don't take notes on this. Just watch, okay? Can you guys see that okay? There, that's better. Let's see. So if I had x plus 2 over x squared minus 4. I don't know. No, not that. Oh, of course I picked that. Okay. So these little thing look like heart monitor races. right? Kind of that's what they look like. Those are vertical asymptotes, actually. This calculator is an older style. Newer calculators won't actually draw the little asymptote in there. But really what the graph is doing is it's going like this. And then it kind of skips this line. And then it starts here. And it goes really close to that. There's a vertical asymptote there. And then it goes like this. Okay? And the reason those asymptotes are there is the equation I had on the... I had this on the top. I had this on the bottom. Right? The vertical asymptotes are whatever makes the bottom 0. So if you think about this, what makes that 0? So if you add 9 over, and then you square root, you get x equals plus or minus 3. And look where these happen. 1, 2, 3. 1, 2, 3. So that's what vertical asymptotes are doing. They're all about what makes the bottom 0. Okay? Horizontal asymptote, there's another trick with that. Okay? That we learn in pre-calculus. I'm not going to expect you to know it right now. Okay? But this one actually has one. And horizontal asymptote we also refer to as the end behavior asymptote in trig. It's all about what's going on the ends. All about the ends, right? So if you look out here, what's this getting really, really close to?
0. Or the x-axis.
Y equals 0, the x-axis. And what about over here? Getting really close to the x-axis. So there's 3 asymptotes in this graph. There's 2 vertical asymptotes, and there's 1 horizontal asymptote. And you get that all from that. I could have told you that just by this. If you just gave me an equation, I could tell you. It's kind of cool. There is another kind of asymptote. I'm going to show you this. I love this stuff. So this is why I love trig. This is so cool. There's another kind. Like if I graphed So right here, I'm going to have x minus 2 on the bottom. So that means there should be a vertical asymptote when x is equal to 2. So in my head, I already expect to see that. Okay? So there's my 2. I have an asymptote right there, right? Oh, I can't see everything. There should be more going on. I can't see it. This is what happens when I make it up. We'll learn more about that later. Anyway, that's a lot of fun. Okay, I totally digressed. Let's go back. Okay, let's refocus. That was fun. You guys are like, I have no idea what you just did. That's okay. All right. How can we tell if we have a growth or a decay? Here's how we can tell without graphing it. So concept summary. So, about exponential functions. So for the function y equals ab to the x, if a is greater than 0 and b is greater than 0, this is an exponential growth function. If a is greater than 0 and b is between 0 and 1, this is an exponential decay. The reason we're only worried about when a is greater than 0, if a is less than 0, it means it's negative. It means it's reflected. And we're not talking about growth and decay then anymore. All right? It's just exponential functions. So for when they ask about growth or decay, your a should be a positive value. And then in the bottom it says, in either case, the y-intercept is when x is 0 and a is our answer. That's always going to be your y-intercept in these cases. The domain is all real numbers. And we have a horizontal asymptote, at y equals 0. So our range is y is greater than 0. Why am I not putting an equal bar there?
It can't be 0.
Because it can't be 0. It's never going to touch it. It's going to get super, super duper close, but it's never going to touch it. So that's why the range is y is greater than 0. So what does that mean to us? I know is the question you're answering yourself. Yes?
So if it has a negative number or a negative sign, would it be y is less than 0?
That would be your range, yeah.
Okay.
Yeah. All right, so let's do an example. Identify each function or situation as an example of exponential growth or decay. What is the y-intercept? So this is example 3. I've gone rogue. Okay. So, what's our a value in this case?
12.
A is 12. What's our b? 0.95. So to tell whether this is growth or decay, we have to look at our b value. Is our b value greater than 1 or between 0 and 1? Between 0 and 1. Because my b value is less than 1, I know that this is a decay. It's going to get smaller. And they also want us to do the y-intercept. And the y-intercept is when x is 0. So anything to the 0 power right here would be 1. So 12 times 1 is 12. And if you looked at the definition above, we know it had to be 0 and whatever your a value is. That's what they wanted from us. For this question, yes. So for b, they give us this function, y equals 0.25 2 to the x. So is this going to be a growth or a decay?
Growth.
It's a growth because our b value is bigger than 1. And our y-intercept is 0. And what's my a value? 0.25. Now C, it's a story problem. So C, it says you start a college savings fund and you start with $1,000. And the account pays 5% interest annually. So, is that going to be a growth or a decay? It's a growth. Because we get to start with 100% of it, but then what do we add? 5%. So what would our b value be? We don't even need to know that. We just need to know it's a growth because it's getting bigger. And our y-intercept is what we started with. So we started with $1,000. We're actually going to learn how to take a story problem like that and write an equation for it. So, all right, are we doing okay? Growth, decay? Okay. Of course, we're going to step it up just a smidgy Rooney. So, that last one led us to something called, we're going to look at growth factors, and we're also going to look at decay factor. The growth value, we would say when b is greater than 1, b is the growth factor. And to figure out, so like in the last example, they said it grew by 5%. So our b would be, we have the 100% we start with, plus, we don't use 5% as a percent, we would change it to a decimal. So our growth factor, if it says it grows by a certain percentage, it's the 100% we start with plus the increase. What if it was a decay? You would subtract your percent rate. So if we're talking about something like this, once again, b is the decay factor, but if we're going to decrease by 5%, our b would be equal to our 100% we start with, but we decrease by that percent rate. We'll formalize that here in a second. So, for exponential growth and decay, here's what the book is giving me. Here's what I'm going to tell you most people are going to say. The only difference is the book is going to use a little a for our initial value. Most people, when they talk about this, especially if you're doing personal finance, those types of things, they use a P. P is principal, and in the business world, principal means what you start with. Okay? So it's the only difference you might see if you talk about this with somebody else in a different setting, is they might use a P instead of a little a. All right? Okay. This big A always stands for the amount after T time. T is time. So the amount is always what you end with. The A, or in most cases P, is the initial amount, also called the principal. R is the growth rate or decay rate. If it's a growth, you're going to have plus R. If it's a decay, you're going to have minus R, because your decay is a negative number. And T is the time. So, of course, we're going to do an example. We're in example 4. So example 4 says you invest $1,000. So the investing $1,000, that's how much we start with, right? So my little a is going to be 1,000. That's what I start with. And we invested at the end of 6th grade. We were very smart. The account pays 5% interest. So what's my R?
Plus 0.05.
And it's a positive, so I'm just going to write 0.05 because we're getting more money. So it says how much money will be in the account after 6 years. So what's the 6? T. So we're going to plug those in and figure out how much money we're going to have. So the amount equals our initial 1 plus our growth rate to the 6. And we use a calculator. So in your calculator, if you go 1,000 and then go parentheses 1.05 and caret 6, why did I change it to 1.05?
Because that's 1 plus 0.05.
Yeah, because that's 1 plus 0.05. 1,000. Okay. What'd you get? Woohoo! I'm okay with that? Yeah? Okay. All right, so last example. Endangered species. Ugh. The table shows the world population of the Iberian lynx. Oh, right. So they say in 2003, there was 150, and in 2004, there was only 120. It's a decay. So if this trend continues, what's the population is decreasing exponentially, how many Iberian lynxes will there be left in 2014? So, what we're going to do is we're going to call 2003 our start year. So we're going to call this our initial. Okay? So for the initial, so that means my little a is going to be 150. Now, what they didn't tell us is our rate of decrease, right? So we can figure that out from our table, though. So to figure this out, what we're going to do is we're going to take where we ended up. So how many linkses do we have right now? 120. And we're going to take away how many we started with. And to figure out the percentage, we divide by how many we started with. So you figure out the difference. So start where you ended. So 120 minus 150 over what you started with. So what's 120 minus 150? Over 150. Negative 1/5, which is, oh, they're decreasing 20%. Oh my gosh. So, now we know what our R is. And if our initial year was 2003, and we want to figure out in 2014, we know what we should put in for our time?
11.
Our T is going to equal 11 years. Is that okay? So our equation is going to look like 1 minus 0.2 raised to the 11. Other questions about where any of those numbers came from? Okay. So 150 and 0.8 to the 11th. Oh, this is so sad.
13.
There's only going to be about 13.
What?
Well, that's so sad.
And what animal is this? Like,
The Iberian lynx. But what do you think is going to happen when people start noticing they're decreasing and they get endangered? They get endangered, get a commercial. No. And so the human factor plays into it. But they're saying if this continued, if this trend continued and it was exponential, sad day. I know. Isn't that sad? Breaks my heart. Okay, I'm done.
Always Josh.
I know. Look. You didn't have any yesterday. So obviously not every day. You know what? I'm going to change that just a smidge-a-rooney. I'm going to go 10 through, I'm going to go 10 through 12. And then 16 through 20. So 10 through 12, I want you to do those three, and then 16 through 20. So I killed off 3 of them for you.
You need graph paper for them.
You will need some graph paper. Oh, but I'm going to add one. No, I'm not. Maybe. Hang on.
Nah, we're good.
Don't whine on me. Don't whine on me. No, I'm okay.